So there's a few things that come up in this week's paper that are super relevant to engineering, of course, since we're talking about control theory. And I just want to show some of the real world applications of that. So this is this little cheap circuit board I got off of Amazon that's supposed to convert 5-volt data signals to 3.3 volts. And vice versa. And just like anything you get off Amazon, you always want to sort of take it with a grain of salt and check it out and see if it's actually doing what you expect it to do. So what I have here is a signal generator that is generating very high quality square waves. These square waves are at a 5-volt amplitude, and I just put it in at 1 kilohertz. That's kind of convenient. So that a square wave is supposed to just be off and then on and then off with an instantaneous change. And so just to check that I'm getting what I expected to get out of here, I'm piping it into an oscilloscope here, and actually the purple channel here is that square wave that's coming out of the signal generator here. And then the yellow square wave here, signal, it's kind of hard to see because the purple is on top of it. But the yellow there, if I turn off the purple, is the about nominally 3.3 volt output that we're getting. If we turn the purple back on, we can see that sure enough, well, this is saying 7 volts. So there's a little bit of a deviation between what we're registering here and what we're registering here, where this is very clean. That's 5 volts. So you could say, you know, what's going on here? And if you take a look, what you can see is that the leading edges, so I'm changing the time domain here, of these square waves are not exactly square. So you can see these little blips that are coming down here. And what we can do is we can continue to change the time domain. So you can see that the frequency is just shy of 1 kilohertz, which we would expect there. But again, we're getting these little blips here. So if I change this here, so this is now 50 microseconds per square here, you can see that it's starting to round off, and we can just zoom in. So we're zooming in on the leading edge here of one of these square waves. And there's a couple of things you can start to see here. So take a look here. This is that 5-volt wave that I'm generating with the square wave generator. It's at 0, it shoots up, but see how it overshoots? And then it comes back down to 5 volts. This is what the Amazon board is generating. So it's supposed to go on this signal from 0 volts to 3.3 volts, but see how it's rounding out? And it's actually creeping up. It's not perfectly square. So let's keep zooming in here on what's happening. I'll reposition that a little bit. If we keep zooming in here, you can see some super interesting behavior. So you can see one thing is that here's that square wave. It comes up, it overshoots, and it comes down, and then it comes in and it hones in here. So this is called ringing. This is a very common situation with a very sharp electronic signal. And what's happening here is that if you look at the Fourier transform or the Laplace transform of a instantaneous increase, it's actually composed of an infinite series of much higher frequency sine waves. And because it's also Laplace, we also have this exponential component. So we have this envelope of exponential attenuation of this high frequency sine component of that signal. So something that seemed as simple as just going from a 0 to a 5 volts is actually quite complicated. You can't actually do that. It's like accelerating to the speed of light. You can't literally go instantaneously from 0 volts to 5 volts. The only way to do that is with this whole spectrum of high frequency components, and you can always zoom in enough to see them. So here we can see that we have this big increase. It's pretty good. We get this overshoot and then this decrease, and then it zeroes in on the 5 volts. That's called the ringing. So what we have is we have the domination initially of the sine wave component of this, which is then dampened down by the exponential decay of that function. It zeroes in on 5 volts. Now that's on the input, and what this is actually mostly due to is the inductance of these wires. So all wires have a bit of inductance, which is a tendency to keep constant current. In fact, often when you're building electronic circuits, you wind little inductors. So you wind wire around these ferrite cores here to make something that has quite a bit of inductance. But all these wires and things like this here, like if I just mess with this, so you can see me just messing with the wires here, I'm changing the inductance here, and it's increasing or decreasing that. So this is really an artifact of me being sloppy in a way that I'm hooking the oscilloscope probes up to the circuit. If I did a better job of that, if I reduced the inductance between the ground probe and the actual signal probe, you'd see a lot less ringing. This here, this increase here, the exponential component, is because there's actually a field effect transistor in here that takes time to actuate. So here's all these little boards that I got from Amazon, and if we open these up, I'll put the phone down a sec. You can see here that there's a whole bunch of little transistors on the back side of these boards, and this exponential component that we're seeing of the signal is the time that it takes that transistor to switch. So the yellow signal here is dominated by the exponential component of this. So this is called the real component, the exponential component, because it's just a decay. That energy is just being dampened out by the system. It's probably being lost as heat in a transistor. And this ringing is called the imaginary component. And that's because it is really due to inductance and reactance, which looks like resistance instantaneously, but that energy isn't being dissipated as heat. It's going into electric fields and magnetic fields that are then returning that energy to the system, which is why we get this bouncing. So these concepts of ringing, which might sound really weird in a paper about cell metabolism, are actually pervasive in dynamical systems. And in fact, it's called ringing not as an analogy to a bell, but because this is exactly what happens when you ring a bell. You're imparting a sudden, instantaneous perturbation to the system. Some of that energy is going to be dissipated as heat, but some of that is going to lead to a deflection of the bell that, due to elasticity, is then returned to the system, and then it bounces back and forth. So you're imparting that single shock which has a bunch of high frequency harmonics that are actually making up that super sharp edge. And this is, of course, exactly what's happening on the rheometer too. When you're imparting forces to a system, you can imagine jiggling a Haribo or another elastic system. You squeeze it suddenly, you impart the shock, it goes, it jiggles, and then that jiggling energy is lost as the energy is dissipated in this exponential envelope here. So once you start looking, you'll see ringing and overshooting and sine waves and exponents absolutely everywhere.